safely. Then they have to pull Orion into the well deck of a Navy landing platform dock ship, just like what you see here now. The partnership that NASA has formed with the US Navy is proving to be invaluable, as they have provided all the necessary support to ensure mission success. They have provided the help of several vehicles, each outfitted with enormous well decks to be able to grapple Orion and pull her inside safely. That monitoring system on board to chart the best course for minimal energy in the well deck. That is to say, we want as few waves as possible. They practice for when conditions are ideal, and they practice for when things go wrong. The mission isn't over until everyone is home safely.
We hope that you will continue to track our progress as we work towards the first woman and next man to walk on the moon. From NASA's Kennedy Space Center for Exploration Ground Systems, that's all we have time for today. We build, launch, and recover for the next evolution in humanity's deep space exploration. And remember, even the sky isn't the limit.
In moon-like environments on Earth, providing valuable input to the design of hardware and strategies to be used by astronauts. Our researchers and partners study and model the sun's flow of energy and particles throughout the solar system, which helps protect astronauts and spacecraft from harsh radiation. The science payloads we develop for NASA's Gateway will monitor space weather conditions from lunar orbit. We also oversee communications networks for NASA, providing two-way support and transmitting critical data. Optical communications will be demonstrated on Orion for potential use on future human spaceflight missions. Reliable navigation on and around the moon will be enabled by proven technology, astronaut location and safety,
that you've seen up there.
Elijah, the Earth is by far the most beautiful thing that I have seen up here in the daytime, at night, over deserts, over the ocean, the clouds, the entirety of it. It's beautiful at this scale to see it with.
Hello, my name is Carter. I'm from California, and my question is, what gave you your first inspiration to want to become an astronaut and travel to space?
What was my first inspiration? You know, I am old enough that I was 4 years old when we first landed on the moon. And I have this memory of my parents taking me out into the backyard, and the moon was coming up over our house, and they pointed up there and said, "We have people there." And I thought that was just the best idea ever. And so ever since I was quite young, I wanted to be an astronaut.
That was absolutely incredible. Victor Glover may be the first person from our community to make it to space, but I can tell that
That concludes the event.
Thank you to all participants. Station.
Awesome. Thank you very much.
Station, we are now resuming operational audio communications.
Copy, Laura. Thank you.
hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Between 1968 and 1972, America conducts human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitation. The upper stage of the SLS is jettisoned, and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
At NASA, we have always answered the innate call to go.
With Artemis,
we are going to stay.
Proving that humanity
can live on the moon,
Mars,
and other worlds,
and share the wonders of the solar system with all.
Our story is one of people.
All those who make this journey possible.
From advocates across communities,
to companies across industries,
to countries around the world,
we achieve this collective endeavor.
Our effort.
But to do that,
we must go.
Hi, I'm Chell Ingram.
My name is Raja Chari.
Kayla Barron.
Kate Rubens.
Hi, I'm Christina Cook.
NASA astronaut Joe Akaba.
Jessica Amir.
Woody Hoberg.
Anne McLean. Stephanie Wilson.
My name is Johnny Kim.
Nicole Mann.
Victor Glover.
Jessica Watkins.
Hi, I'm Matthew Dominic.
Jasmine Mogbelli.
Frank Rubio. Scott Tingle.
This is what we do. This is what we will do.
Let's go.
We go to the moon to learn how to live on other planets.
For the benefit of all.
Space Launch System is the next newest, biggest rocket that we're going to build, and it's not just a replacement for the space shuttle. This rocket is going to carry us much further than the shuttle would go. It's NASA's next big rocket for deep space exploration.
The SLS is a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had 2 kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes, and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now, the inventory that we've got consists of 14 engines that have flown on shuttle. We've got 1 engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that will be able to use for flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just, delivered the first crew module to the ONC building at KSC. We've started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those parts, within, thousandths of an inch to make sure that everything is going together okay.
Putting, wiring inside of it, putting tubes for the, for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the ONC building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the ONC, and so their little shop delivers to the big shop.
Thermal protection is very difficult in re-entry vehicles to test and to model. I mean, really, you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20 by 20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router, it could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
The other component is the heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up the carrier structure itself.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCB or Orion.
In order to adapt for the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle till splashdown, and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the fire room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launched from the mobile launcher, and not only launch from the mobile launcher, but have a on the mobile launcher. The vehicle will be assembled at the vehicle.
When the mobile launch platform had a tower on it, we knew that the VAB could remain adaptable and accommodate hardware, the new vehicle access with that new platform.
The vehicle is ready with all the connections. The only thing we got to do is move the vehicle to the pad, do the connection.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket, and things along those lines. And that goes from the crawler, lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinders. Last November, we actually took a ride out with the completed crawler 2 out to the pad and tested out the systems and a couple punchless items, but everything worked great. The control system had been upgraded. The driver's cabs consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it. The traction support elements, each of the 4 corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those, enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward. And NASA has a big following, and every time I talk to people, they're excited about NASA.
Enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
This is probably the most exciting point in the program from the standpoint of activating the factory. The stage of the program that we're dealing with is called confidence hardware, and that's when we take flight form hardware, run it through all the tooling, use that for subsequent testing and fit-ups. All of the tooling that is going in is upsized to scale for the SLS program. Some of the vertical tooling is in a building that is probably 15 stories tall. The largest section of the rocket is the fuel tank, the hydrogen tank. You have to stack that with the other sections of the rocket, inner tank, the engine section, the forward skirt, put all that together, and you've got a very large rocket. We're looking at completing the first flight vehicle at MAF in May of 2016, and we're on track for that.
SLM is selective laser melting. It's a method of turning powdered metal, finely grained powdered metal, into solid parts. The design is done straight from 3D CAD models, which is standard in the industry. You can use any kind of commercial software, and the machine takes that and cuts that into a bunch of slices and builds them slice by slice. What we have to do in order to trust the material is we have to do a lot of testing on the ground. Back in 2011, we built a duct using this process for the J2X, and we hot fired it. And what we saw was basically no deterioration of the material. We built the one part for 35 cents on the dollar. More complex parts, we think the cost savings approaches an order of magnitude. If this technology proves out like we think it will, the schedule savings and the cost savings is almost beyond imagination.
The work that we're doing here is to support the Orion test flight, which is EFT-1. The hardware that we're manufacturing here in this shop is the adapter for the Delta IV launch engine to the Orion test article. To complete the welded structure, you have 3 vertical or longitudinal welds that join the barrel panels into a cone. It moves from the vertical weld tool to the robotic weld tool for the circumferential welds. The circumferential welds are the welds that join the welded cone structure to the forward and aft ring flanges, and that pretty much provides your primary structure.
We within NASA are passionate about STEM.
SLS was at Tennessee Tech for Engineering Week. We sat on a panel and we did video talks with several different elementary, middle, and high school students.
Their Engineering Week, they have shared with us, usually draws about 70 people. And on a Friday night, one of our programs drew more than 400. The more that we can get people involved in those creative ways, the more successful we're going to be.
The outreach for inspiring the future is such an important goal of NASA's.
So we have to foster that inspiration and that dedication to learning that's necessary in order to keep NASA's dreams alive.
There's a lot of work going on the VAB getting ready for SLS and Orion coming in 17. In the VAB, we built a full-scale mock-up. The main thing we're looking for is the handling and access. What we're looking at is getting some of the ogive panels from the GTA, which is the ground test article. They work great to do the practicing just like we used to see them in the labs. We are working pretty heavy on the EFT-1 part, and we're only 18 months away. The whole program, it's NASA successful. It's not just ground systems or Orion or SLS. So even though they're going off of Delta IV, having this flight successful does help SLS and GSDO. It's going to give us a lot of experience.
We did a one-year design on the entire crawlerway from the VAB to Pad A and from the VAB to Pad B. Over the years, the top-level rock has been refurbed multiple times. The actual foundation, the lime rock, which is what we're doing now, hasn't been refurbished since it was installed. We are reinstalling lime rock and bringing it back to print, and then we'll install some fresh river rock on top, and then hopefully be good for another 50 years. Currently, the contract is about 20% complete. We're looking for a total completion date in mid-2014. The crawler transporter, as it finishes its upgrades, it will exercise or stretch and go up and down the crawlerway.
We have almost 47 different projects that touch almost every system on the crawler. The driver's cabs, the brakes, the generators. We're increasing the generator capacity so we're able to provide more power to the mobile launcher, to the vehicle, to the spacecraft. Within the next 2 weeks, we're going to be able to take the belts off the crawler, remove the old assemblies, and start assembling the new components in place, followed by the gel cylinders, the hydraulic cylinders. What the gel cylinders do when you're carrying a load, they automatically keep the crawler completely stabilized so the vehicle does not see any movement, especially when you're going up the ramp. After we complete the modifications, we'll be able to carry over 18 million pounds.
18 months from launch is not very far away, really, in the grand scheme of things. You think about trying to get all the systems on board. The guys are going great guns at putting all the secondary structure in, which absolutely has to be done right before they start putting the systems in. But you think about still all the wiring that needs to be done and all the plumbing that needs to be done and welded. Back in November, we had an issue. We took the pressure vessel to proof. We had a crack generated in the primary structure. So it was sort of all hands on deck, if you will, to go figure out what happened and why and how to fix it. And so we went in and just basically the guys created some fittings to offload the cracked part of the structure, and then the technicians at the ONC went in and cut the cracks out, and they're in the process of putting that all together now. So it'll be retested in April. For the next few weeks, we'll take a little bit of a backseat to getting the crew module through its big structural test. Then the structures guys will put focused attention onto the service module, getting it finished and built up, and then it goes through a structural test as well.
CPAS stands for the Capsule Parachute Assembly System. We are doing the development of the parachute system for Orion. The military have developed a technique called low velocity airdrops, and they set up the conditions for which then to start the sequence of the Orion parachute system. And so we work very hard to reduce the risk as much as we can, to understand as much as we can, in order for when we do fly this crew, it's going to be a safe vehicle. So over the next 6 months, very happy that we will be delivering our parachutes to the Cape, to the ONC building to be installed in the EFT-1 vehicle.
The NBL, we're kind of working on everything post-splashdown. We're working with the folks out of KSC and out of Patrick Air Force Base, and with Navy divers out of San Diego, putting together training material on how to actually go recover EFT-1 out in the ocean. We're using Navy amphibious assault ships, and what they do is they can ballast down and lower the back end of the ship into the water, and we can hook the capsule up and just tow it into that well deck and set it down in a cradle. There's about 17 folks when we get a dive crew available. So what we'll do with them is we'll put 2 sets of 3 in small Zodiacs, and they'll do all the hands-on work on the vehicle. The cradle that we plan on using for recovery, it'll be finished within the next 30 days. We're delivering it out to Langley. And then in August...
There was always a hope that I would be working on a vehicle that would carry humans farther outside of low Earth orbit, getting back into the roots of what NASA was built on, which is exploration.
What could be more exciting than building the next great outreach for the U.S. government and for mankind, actually?
You have to let people know that we're still here. Oh yes, shuttle did retire, but we are still making progress and we are still moving forward.
NASA's nowhere near slowing down. We're preparing for the future.
It's a great time for us to have such a tangible artifact of the work and the hours we put in. So yeah, we're really looking forward to EFT1. It's going to be good.
Very rarely do you get the opportunity to kind of literally from the ground up put together a factory whose sole purpose is to go make history and do exciting things for not just NASA, but for America and for the whole world.
We're in the process of getting the factory ready for SLS production. And in that process, there's a series of new tools that we've been installing in the factory.
Now we have not just put in new tooling, there's some legacy tooling that we're using. Most of the external tank buildings are being reused. We have a lot of construction going on for those, getting ready for a rocket that's same diameter but a little bit longer.
Not only are we using the legacy knowledge, the lessons learned, we're also incorporating new technologies.
The tool today is in the vertical friction stir welding center, and its job is to produce the cylinders that make up the parts of the tank that'll be stacked.
And that is going to be the tool that joins every panel on every barrel for the rocket.
This device will actually do the weld in a single pass and then also do inspection. So these are the large barrel sections of the core stage that will be the foundation or the beginning rocket that will actually take our crews beyond the moon and really propel us into space.
Here at Marshall, we've designed the interface hardware in between the Orion capsule and that upper stage.
The MSA, I think, is a great example of a couple things. One, it's actually a piece of hardware that we're flying on an early test, but we're also going to fly for the long term. And so this is the same design that we'll use when Orion's on the SLS and we're actually flying people.
Today, we've been taking the two unique pieces of hardware that are supposed to have a common interface, basically lowering them together, bolting, and making sure that they fit.
Well, we're going to test a lot of the key systems on Orion and also for SLS with the upper stage of the MSA that are going to be used when we fly people into deep space.
Most recently, we've been involved with NASA with the SLS development using our unique forming technology along with our other core processes in terms of machining, welding, heat treating, and inspection technologies. Really is a one-stop shop is what the way you would describe it.
Right behind me you have the first weld development cap, or I think you call it the weld confidence cap. The production order will start deliveries in 2014. Spacecraft also builds the domes for the upper stage Delta IV vehicle, which will be used for the EFT1 flight, as well as the first two production flights of the SLS program.
For the SLS PDR, our primary role was the overall communication and outreach support that we provide back to Todd May's office for SLS. We provide all of the communication support for that particular team, that program and project.
Well, it's a preliminary design review, and primarily it's a technical review to make sure that the design is acceptable and at the appropriate level of maturity.
There's a lot of discussions, there's a lot of meetings across the board from technical, cost, schedule, performance data, safety, human factors.
It's like a health check on the program. Those of us that are working on the program, we've got our head down, we're doing our pieces, and sometimes when you're working real close to things, you don't necessarily see everything.
So there's so many moving parts and so many things going on at the agency, as well as the center, that to show people that we are moving in the right direction, to pull together the complete story of where we are as a program.
Watching at it from a higher level headquarters viewpoint, it's just gratifying to see the accomplishments that the teams have made and continue to make every day.
For CT2, we're doing modifications not only to make it last another 20 years, but also to uprate the load capacity. The main project we're working on right now is the roller replacement project, which is the roller assembly. It's actually the rollers, the shafts, the bearings that support the crawler. Actually, if you go there, you'll see trucks A and C jacked up,
and on cribbing. And that's the first time in the career of the crawler it's ever actually been jacked off the ground. So the guys have easy access to the roller assemblies. And they're in the process now of removing the old rollers, old shafts and old parts. Once they've done the line boring, that's when they'll start assembling the new rollers and the new shafts and the new bearings and the new sleeves and new adapters and new plates. So there's quite a bit of work, and that work will go well from August through October. So there's going to be a lot of trucks delivering a lot of steel here at Kennedy.
We started actually the new design for flame deflector as well as refurbishment of the flame trench, and that's because of the new requirements for SLS and commercial vehicles. We've started the demolition of the flame deflector. We've got concerns of, due to age and the debonding of the flame trench structure, this would possibly be a safety hazard for, our new program. And that's why we had to go in and do a new design and refurbish this flame deflector and flame trench.
These pieces here, they're not just one program, it's not just one mission, it's part of a capability that will enable this country to be a leader in space, to continue to take people from the Earth well beyond low Earth orbit out into deep space. And this is the hardware that will do that over multiple decades in the future.
So the work that's been accomplished so far is primarily structural type work, right? It's a lot of drilling, a lot of secondary structure installation, mechanical structures, the support structures. The next step is starting to install the subsystems. When we actually perform the welding on tubes for propulsion and the environmental controls and life support systems, those have to be at a higher level of cleanliness. When you look at the facility, there are these very large walls that are on the perimeter of the structure itself, and those are called HEPA filter walls. We can perform clean room work for the tubing concurrently while on the outside doing more standard clean room. So our goal is next summer sometime to turn the vehicle over, early summer, over to the ground operations organization so they can start their processing.
Well, the service module is attached below the crew module, and it has the prop tanks and the engine, radiators, solar panels. The service module, it all came in pieces. There's 49 composite panels where SAM returns to Earth.
We performed two primary tests so far. The proof pressure test, which is just the pressure vessel, and that is put into the proof pressure cell. It's pressurized and a relatively high pressure. We're testing how well the vehicle was built. And then the follow-on test is the static loads test, where the vehicle goes through 8 different loads test cases. And so the vehicle is put under pressure, it's put under tension, it's put under compression. The whole intent is to simulate similar conditions that the vehicle would experience, say, in flight, in launch, and also in landing and recovery.
We usually get the abort motor first, and for this mission, the abort motor is inert, being a nominal flight.
We're going to have instrumentation on it to, again, understand more about the loads and environments that we expect to see in flight, but it will be an inert propellant that's cast into the motor.
This time we got the jettison motor next, and that's the only live component of this vehicle. We do a nominal jettison, the jettison motor fires, the last separates from the CM, and the CM continues on its mission.
One of the challenges of any new system is understanding the loads as you ascend up through the atmosphere and the dynamics, the acoustics, and we'll be able to gather a lot of that information.
The back shell, it looks, though it looks the same as what we flew on shuttle, it is different. We kind of took the best aspects and put them together to meet Lockheed Martin's requirements for the Orion capsule. Two major things we're trying to accomplish here. One of them is to prevent micrometeorite damage when we're on orbit for long duration. The other, of course, is the reentry aspect. The skin that you see on the capsule, what you would see on orbit, sits on top of a composite substrate, what we call the back shell panel, that when combined together gives you the complete back shell. There's some sections that have some very complex geometry. So what we're going to do for the first time is take a substrate that's built by Lockheed Martin and put it together with the tiles that are manufactured by Jacobs and validate the fit up. Like any test vehicle, you're heavily instrumented. We're going to come back with a tremendous amount of data on how the system performed.
This first flight test of Orion is really to understand how the heat shield performs, and that heat shield's going final manufacturing at Textron.
Textron's had a long association with NASA and working in the space area for space protection.
The technology today has advanced tremendously. Our manufacturing technology has advanced, but ironically, we're still using a material that has proven itself for the last 40 years.
Avcoat is a very efficient ablator, and as an ablator, what it does, it allows us to protect the capsule from the high heating that occurs during re-entry.
There is no material, non-ablator material that can handle that kind of heat. You have to shed away the heat. Basically what you're doing is you peel off the layers of the heat shield, you're taking heat with it.
When we apply Avcoat to the heat shield, we bond the honeycomb onto the carrier structure, and then we inject the Avcoat ablative material into the cells. The honeycomb acts as a crack arrestor and gives it rigidity and strength as a whole.
We know we're on the critical path for the Orion program, and so our employees are literally working all hours, all days of the week to make sure that we hit our schedule. We know there'll be more heat shields coming, and we're very excited about that. Our job is to make sure they're perfect.
The development programs I find just awesome, because this is where you're coming up with the new ideas, you're creating the new vehicles, you're pushing the boundaries in essence.
You can feel that we're going to go do this. The hardware is starting to come. The Orion hardware is getting ready for its first flight test down at the Kennedy Space Center.
The excitement is here. We are really ready to get going. So we are far from being out of space. We are really getting ready to go into space.
That's so rewarding to see our focus into what's next, because this really is our future.
I know the day that we fly this thing, there are going to be thousands of people that are going to be excited that are working on this, and the NASA workforce and the contractor workforce. We're going to be proud of the work that this team has done, and I think we're going to be proud of our country too. It's going to be a pretty exciting time.
I'm ready to build a rocket, and we are ready, and we want to build it on time.
It was a busy third quarter for NASA's Exploration Systems Division. The first liquid hydrogen tank barrel segment for the core stage of America's new Deep Space Launch Vehicle was recently completed at the Vertical Weld Center at NASA's Michoud Assembly Facility in New Orleans. The segment is considered a confidence barrel segment because it validates that the Vertical Weld Center is working the way it should. When all segments are complete, the 212-foot core stage will be assembled in the Vertical Assembly Center, now under construction. In August, a 31-inch scale model of the SLS core stage B2 test stand was successfully tested in a wind tunnel. The actual B2 test stand, located at NASA's Stennis Space Center in Mississippi, was originally built to test Saturn rocket stages. The stand is being renovated to enable testing of the SLS core stage. The core stage, with 4 RS-25 rocket engines, will be installed on the B2 stand for propellant fill and drain testing and 2 hot fire tests in late 2016 and early 2017. In August, the largest 3D printed rocket engine component ever built by NASA, an injector, was tested during an engine firing that generated a record 20,000 pounds of thrust. 3D printed engine components. In September, the Orion stage adapter diaphragm arrived at the Marshall Space Flight Center to undergo pressurized testing before being integrated with the spacecraft's stage adapter, certifying it for flight conditions. The component is an integral part of the stage adapter that will connect Orion to a Delta IV Heavy rocket for NASA's Exploration Flight Test 1 in 2014. The diaphragm, a lightweight composite structure, serves as a barrier between the upper stage of the launch vehicle and the spacecraft, preventing hydrogen gas buildup from the rocket beneath the spacecraft before and during launch. At Florence's 21st century space launch objectives. A new universal flame deflector and trench will be completed in early 2015 and will support the new Space Launch System rocket and possibly a variety of commercial launch vehicles. For more than a year, NASA's Crawler Transporter, CT-2, has been undergoing a major tune-up in KSC's Vehicle Assembly Building. The crawler modifications are designed to enable the vehicle to transport heavier launch vehicles, including SLS, to the pad. Once the roller bearing work on half the crawler is completed, it will be prepared for a test rollout scheduled for January 2014. After traveling 3,600 miles above the Earth during the Exploration Flight Test 1 mission in September 2014, Orion will splash down in the Pacific Ocean, where it will be recovered with the help of the United States Navy. In August, with the Navy's USS Arlington stationed against its pier in Virginia, divers in small boats led the test capsule to the flooded well deck of the ship. With the capsule in position over the recovery cradle, the water drained until the capsule settled. Navy divers prepared for the recovery test in Norfolk by training in the 6.2 million gallon pool at NASA's Neutral Buoyancy Lab near the Johnson Space Center in Houston. In July, the Orion team successfully conducted the parachute test vehicle PTV-5 airdrop test at the U.S. Army's Yuma Proving Ground. 17 parachutes were deployed during this test. 9 were test technique related and 8 were the Orion system parachutes. At the Operations and Checkout Building High Bay at the Kennedy Space Center, the Orion team completed hundreds of welds and installations for the spacecraft's propulsion, life support, and environmental control systems. At the Johnson Space Center in Houston, NASA Administrator Charles Bolden welcomed 8 new astronaut candidates. This group will be among those who may carry out the first ever human missions to an asteroid and onto Mars. In October, recorded Orion telemetry was successfully transmitted between the Mission Control Center in Houston and the White Sands Communication Facility in New Mexico. White Sands will be used during the EFT-1 flight to receive and retransmit the Orion spacecraft telemetry. In late September, NASA astronauts Rick Linehan and Mike Foreman tried out a prototype display and control system inside an Orion spacecraft mock-up at Johnson Space Center during an Orion ascent simulation. Over the course of 2 weeks, 10 crews of 2 astronauts each performed launch and abort simulations inside the Orion mock-up to fine-tune the design of the displays and controls.
As 2013 wound to a close, NASA's Exploration Systems Development Division powered through an array of tests and milestones. Vehicle manufacturing, facility construction, and systems testing for NASA's all-new Space Launch System are progressing rapidly. Meanwhile, Orion and the Ground Systems Development and Operations programs prepare for the upcoming launch of Exploration Flight Test 1. The Orion Stage Adapter Diaphragm is a lightweight composite structure that protects the Orion crew capsule from hazardous gases produced by the upper stage engines. The diaphragm was recently pressure tested by joining it to the adapter and sealing with a vacuum. This pressure test simulated atmospheric conditions the hardware may experience during flight and is another essential milestone to ensure crew safety. The Space Launch System's Adaptive Augmenting Control System was tested at the Armstrong Flight Research Center in November. To test the system, SLS's automated avionics computer was installed on one of NASA's versatile FA-18 jets for analysis and validation. The Adaptive Augmenting Controller is an autonomous course correction program designed to instantly detect and adjust to unpredicted changes in flight.
Copy, disengaged.
By exercising the system in an FA-18 research jet, engineers were able to run dozens of scenarios on each 90-minute flight. Successful deployment of this innovative control system will increase performance and robustness of the rocket as it is steered along the path to deep space. At Michoud Assembly Facility, the first propellant tank dome was completed on the circumferential dome weld tool. The massive propellant tanks used on the SLS core stage are unlike any that have ever been made before and require new tools and processes for construction. The nearby Vertical Assembly Center will house one of the world's largest friction stir welders, which will be used to assemble the liquid hydrogen and oxygen tanks. Last November, 90 trucks poured 900 cubic yards of concrete foundation in preparation for the new Vertical Assembly Center's tower structure and welding elements. This amount of concrete is similar to a foundation for a major modern hotel and will accommodate one of the largest welding tools in the world. With the launch of Exploration Flight Test 1 less than a year away, the Orion program is conducting more frequent, critical testing. In October at the Kennedy Space Center in Florida, the avionics system was installed module and powered up for the first time, carrying Orion's most critical safety component, the ablative heat shield. The world's largest and most complex heat shield will protect future crews as the capsule plummets through the Earth's atmosphere, traveling more than 20,000 miles per hour. The heat shield will experience temperatures nearing 4,000 degrees Fahrenheit. Orion's service module was lifted for a test fit to the spacecraft adapter it will use on Exploration Flight Test 1. With the help of an air-bearing pallet, the adapter was positioned beneath the service module for alignment. A modified version of Orion's launch abort system was completed for the spacecraft's first mission. The launch abort system consists of 3 motors: the main abort motor, the attitude control motor, and the jettison motor. Because Exploration Flight Test 1 is an uncrewed launch, only the jettison motor of the abort system will be used to separate the structure from the crew module. Across the country, in Sunnyvale, California, Lockheed Martin conducted secondary testing of the fairing panel separation from Orion's service module. These 14-foot-tall protective panels will be jettisoned after the craft reaches an altitude of 560,000 feet. Each panel has 6 breakable joints that fire apart, followed by 6 explosive separation bolts, sending them safely away from the capsule and service module. Lockheed Martin also successfully conducted the first of many forward bay cover jettison tests. After Orion completes it to deploy. At KSC's Vehicle Assembly Building, engineers test fit 4 ogive panels to the Orion ground test article. These 4 panels will cover the Orion capsule during launch and attach to the launch abort system. The ogive panel confidence fit was one of many tests designed to simulate the procedures for manufacture, assembly, and stacking. Although NASA and the U.S. Army may seem like unlikely collaborators, both agencies face the same challenges of keeping their men and women safe from chemicals and explosive projectiles. This mutual interest led to NASA's acquisition of 4 mine-resistant, ambush-protected trucks for use as emergency escape vehicles from Launch Complex 39. The 40,000-pound MRAPs came from Red River Depot in Texas and will be ready for use after some minor modifications. Launch Complex 39 is also getting an upgrade to its mobile launcher. The 405-foot steel tower is being reconfigured and strengthened to accommodate the weight, size, and thrust of the SLS vehicle. After a successful year of construction and testing in 2013, NASA's Exploration Systems Development Division looks forward to its biggest test yet, the flight of EFT-1 in the fall of 2014. Halfway through one of the most productive years in recent space history, NASA's Exploration Systems Development Division is moving humans ever closer to deep space exploration. The Space Launch System, NASA's next-generation deep space launch vehicle, had an intense spring full of development and testing. Testing on the avionics system, responsible for controlling the Space Launch System's solid rocket boosters, began in April. The avionics system will ignite, steer, and jettison the two solid rocket boosters and will continue to undergo an extensive series of tests this summer. In May, structural tests on the SLS booster forward skirt proved it could withstand millions of pounds of launch stress during a series of ground tests. The SLS core stage will be powered by 4 RS-25 engines that are now undergoing preparation for test firing at the Stennis Space Center in Mississippi. Following initial testing, the engines will be integrated with the core stage, and the entire assembly will be tested on the B-2 test stand. Because the SLS core stage is 50% longer than the Saturn moon rocket stages, the mothballed B-2 test stand and the main derrick crane are currently being modified and upgraded to accommodate this enormous structural element and powerful main engines. Production on the core stage structure and propellant tanks continues at the Michoud Assembly Facility in Louisiana. 34 primary structure components and 20 rings have been welded to build the core stage propellant tanks, including 9 barrels and all the rings needed for SLS's first flight. A 5% scale model of the SLS was ignited to test how both low and high frequency sound waves will affect the rocket as it fires its solid rocket boosters and main engines on the launch pad prior to liftoff. These ongoing tests are collecting data from over 200 sensors to study the acoustic impact on the spacecraft and verify the design of its water-based sound suppression system. A major milestone in the effort to transform Kennedy Space Center into a multi-user spaceport was met when Ground Systems Development and Operations completed the initial design and technology phase of the preliminary design review. GSDO is modifying the spaceport's infrastructure to support several different spacecraft and rocket launch needs. Firing Room 4 at the Launch Control Center at Kennedy Space Center in Florida is being renovated into 4 separate launch areas to serve NASA and commercial users' needs. Designed to accommodate a multi-user spaceport, the new adaptable rooms can open up to give more space as needed by a customer's launch room parameters. Upgrades to the mobile launcher at Launch Complex 39 are underway, with significant progress toward advanced usability. GSDO is systematically modernizing the launcher to meet the increased needs of the more substantial Space Launch System. Upgrades include structural work, an improved sound suppression water system, a redesigned exhaust opening, new data connectivity to the Launch Control Center, and updates to the power, air condition, and fire alarm systems. After the Exploration Flight Test 1 mission is complete and the capsule lands in the Pacific Ocean, the Ground Systems Development and Operations and Orion programs and the U.S. Navy will retrieve the capsule and ship it back to Florida for reuse. The return process requires a series of pre-transportation operations, which were successfully tested in May. Workers practiced assembling a transportation fixture that will be used to move future Orion crew modules across the country. The newly renovated Flight Control Room at the Johnson Space Center in Houston played host to members of the media and top NASA officials in April. The White Flight Control Room will support the Orion spacecraft during NASA's deep space exploration missions. In May, the room was used in a joint integration simulation, along with a team at the Kennedy Space Center in Florida. The two teams simulated the pre-launch and in-orbit phases of Orion's mission and solved real-time problems, acting as the eyes and ears of the uncrewed spacecraft. The rigorous testing on Orion's parachute system continued in April and June, proving the parachutes are capable of surviving potential failures during both re-entry and launch abort scenarios. The first test simulated an abort scenario by dropping the capsule from a height of 13,000 feet and releasing the main parachutes before the drogue parachute could deploy or the vehicle could straighten itself out. The second test pulled the capsule from the C-17 airplane at an altitude of 35,000 feet, with one of the main parachutes intentionally rigged to skip a crucial phase in the unfurling process. Both tests demonstrated the parachute system can tolerate unexpected failures and still carry the capsule safely to the ground. After 2 years of intense production and testing, Orion's massive heat shield was successfully attached to the crew module in Kennedy Space Center's operations and checkout facility. The 16.5-foot wide ablative shield will protect the capsule from re-entry temperatures of up to 4,000 degrees Fahrenheit. A center of gravity test confirmed that all of the ballast was properly installed in the crew module. The test validated the Orion team's computer models used to calculate the amount and location of ballast needed to properly balance the crew module. With the heat shield securely attached to the capsule, the crew module was then stacked on top of the service module in June. The stacked modules will undergo electrical, avionic, and radio frequency tests to prepare for the Exploration Flight Test 1 in December. In May, astronauts at the Neutral Buoyancy Laboratory in Houston trained underwater in newly modified spacesuits to work through simulated operations for NASA's asteroid retrieval mission. A month later, a naval team worked with Orion recovery specialists to train for a set of procedures to safely retrieve the capsule and forward bay cover. As Exploration Systems development closes in on December's launch of Exploration Flight Test 1, NASA centers nationwide stride toward the Moon, Mars, and beyond.
Hi, I'm Serena Anand-Chancellor. I'm a NASA astronaut, and this is Ask NASA, and I'm ready for your questions. All right, so first question. What is Artemis, or what is the Artemis program? So the Artemis program is our lunar exploration program. We will get to the South Pole of the Moon by 2024, landing the first American woman and the next man. Why are we doing this? Well, in order for us to head towards Mars, we need a special place where we can practice, essentially develop robust engineering technologies, figure out how well the human does with long-duration spaceflight, learn how to build habitats, and we do all of this on the moon. Essentially, we practice. It's an engineering battleground, so we can go to Mars. What do you think it'll be like to go on an Artemis flight? Well, let me tell you, this would actually be really cool to go on an Artemis flight because we'd be heading to the moon. Now, what vehicle will we be traveling in? Well, it's actually the Orion vehicle right here. And some of you may recognize this. This is similar to the old Apollo capsules, but it is bigger, it is better. I've actually climbed inside the mock-ups, seen the systems, very modern systems. This is what will be taking us back to the moon. It's going to have the first American woman on the moon.
Serena, did you always want to be an astronaut?
I did, probably since I was 8 years old. My dad finally asked me one day, do you want to be an astronaut? And I said, yes.
What one personal item did you take to space?
Oh, I took multiple personal items. It wasn't just one. Funny enough, I took a back scratcher because you need a back scratcher wherever you go.
What food would you take to the moon?
Oh, easy. Cheeseburger, French fries, every time.
Yum. If you were to dance off with an alien, what song would you pick?
That's easy. It'd be Michael Jackson's Billie Jean. We played this song on the launch pad.
What do you miss the most about Earth when you're in space?
I missed feeling the earth. So I miss the wind, I miss the rain, I miss the smell of the earth, the smell of the grass. These are things you just can't imitate on station.
Is it scary being in space?
It's not scary being in space. I mean, it's your home, and it's the size of a 5-bedroom house. It's absolutely huge, and your friends are up there with you, so what's better than that?
Do you know how cool you are? Because we think you're amazing.
You know, as my husband says, I still take out the trash like everyone else.
So you're a doctor. Can you fix this man?
Well, I'm an internist, not a surgeon, but I will try. Ooh, I've got to do this carefully. I don't want to set off. Yes. Yes, see, so now. Nope, that's it.
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
February 16th. That marked a major milestone, firing all 4 RS-25 engines together for the first time for about a minute. However, it ended earlier than planned, so NASA and Boeing decided to do a second test. Teams have been working hard to get to this point, and the test countdown actually started a couple of days ago. Here to update us on where things stand is NASA Public Affairs Officer Catherine Hamilton and Headquarters Green Run Manager Bill Robel in one of our test control centers here. Catherine?
Thanks, Lee. We're inside a secondary test complex outside of the control room, and we're listening in to provide you updates as the team progresses through their steps for this operation. We believe we're within about 45 minutes of the hot fire. The team actually started 2 days ago powering up the avionics on March 16th, and they checked out all the systems that they had tested on previous tests. Earlier this morning, they conducted a go-no-go poll to proceed into the test, and I have Bill Robel here with me to tell us a little bit more. Bill, can you tell us about how the operations have progressed today?
Yeah, sure will. So at this point, we've been in kind of replenish mode for both the liquid oxygen and liquid hydrogen. We've got, at this point, 540,000 gallons of liquid hydrogen on board and another 200,000 gallons of liquid oxygen on board. And they're in the conditioning process right now where we're trying to get that temperature down as low as we can, get it within the start box. And we're also doing the same thing on the engine side of things. And what's important about all of this is that, this timeline that we're going through here will help inform the operations that'll take place down at Kennedy Space Center, where not only do they have these things to worry about, but then they've also got to do the things where they're getting people on board and taking care of all the other extraneous things that they have to do down there. So for us here, right, we've also been monitoring things like the battery charging. They're basically up to speed at this point. And then we've got the redundant inertial navigation unit wet checkout, which is basically mounted up in the LOX dome area. And so they're looking to see how it behaves relative to the low temperatures that we're seeing now in that compartment. And so at this point too, the teams are basically looking at all their data, making sure that their systems are where they're supposed to be and ready to go for proceeding into the terminal account.
Thanks, Bill. And can you tell us a bit how the timeline is different for today's test than for a launch, and how is determining the time of the hot fire different from setting the time for a launch?
Yeah, so for us, it's actually we're in a pretty good spot. We're trying to at this point maximize the amount of commodities that we've got here in the test facility. So we're playing a little bit of a game where we've got crews that have been on for a number of hours, and at 12 hours roughly, they'll time out. We want to make sure that we don't have to end the operation any earlier than that, so we're really trying to maximize that. So they're in the process of working that with the nitrogen and helium, liquid oxygen, and liquid hydrogen. The other part of it is, right, the beauty of us is we're in a test. We're not going anywhere today. And so we don't have a destination. Our destination is right here. And so the difference right at Kennedy is they've got, the orbital mechanics, their destination as to where they're going to go. And so they have to work basically all those details in to their exact launch window. Our launch window is basically when we start the test, and that doesn't matter too much today. But they do have they've got a real time hack that they have to hit. So they'll have built-in holds into their process and procedures down there, and that'll inform them kind of how they move through the next steps. We just are fortunate we don't have to worry about that today.
Great, thanks. So that means that we don't have a specific hot fire target time right now at this moment, but we'll keep listening in and we'll provide updates. We do know that the test remains to be projected within the test window, and we believe we're within about 45 minutes. And so we'll continue to listen in here, and I'll turn it back to Lee.
Thanks, Catherine and Bill. And we will come back to you in just a few minutes, like you said, to take us all the way to the test, or sooner if you have any updates for us. We will be listening in, and I'll head right back to you if you do. Now, if you are just joining us, welcome. We're live at NASA's Stennis Space Center in Mississippi, and we're following the second Green Run hot fire test of the Space Launch System rocket's core stage. The core stage is the center core of the rocket that includes 2 propellant tanks and 4 RS-25 engines, miles of cables, all of the avionics, electronics, computers, the brains of the rocket, and all of the plumbing that work together to launch the rocket during the first 8 minutes of the mission. The green in Green Run refers to new, untested rocket hardware. So this is a comprehensive series of tests of all the core stage hardware for the SLS rocket to demonstrate it's ready for launch, culminating with today's hot fire. The core stage will power every SLS mission. So this test is important not just for Artemis 1, but for all future SLS launches as well. Those RS-25 engines are expected to fire up shortly here at Stennis Space Center. Before that happens, let's get a closer look at the Space Launch System rocket. Super heavy lift rocket and provides the foundation for human exploration and scientific missions to the moon, Mars, and beyond. Miles in just over 8 minutes, offering more energy, volume capacity, and payload mass than any rocket built today. Under the launch abort system, Orion, and the upper stage, and between 2 solid rocket boosters is the heart of every SLS configuration. The core stage, towering 212 feet with a diameter of 27.6 feet and storing 537,000 gallons of liquid hydrogen and 196,000 gallons of liquid oxygen. This is the world's largest core stage ever built. The core stage for Artemis 1 fires up for the first time at NASA's historic B-2 test stand. The core stage was designed by NASA's SLS program at our Marshall Space Flight Center in Huntsville, Alabama. Then built by lead contractor Boeing, using state-of-the-art manufacturing just down the road at NASA's Michoud Assembly Facility in my hometown, New Orleans. It includes engines manufactured by Aerojet Rocketdyne, with contributions from more than 1,100 large and small businesses in 44 states. It was shipped up here to Stennis on the Pegasus barge in January of last year, and then installed on the B-2 test stand where you see it here today. Engineers then began activating the stage's components one by one and taking it through the series of tests that make up the Green Run over the past year. Each test built upon the previous one and added a little more complexity. So today's hot fire builds on all of that work for a full test of the entire integrated system that will simulate all parts of the core stage working together during launch. Today's test will take us from extreme cold to extreme hot as the team loads cryogenic or super cold propellants into the fuel tanks and then fires up the engines to drain the propellant from the tanks to simulate launch. Now, the hottest part of the test today will be those 4 RS-25 engines at the bottom of the core stage. These RS-25s we are testing today are repurposed from the shuttle program. These 4 engines flew on some pretty iconic shuttle missions, including one of the Hubble Space Telescope servicing missions, the historic return to space of Mercury astronaut and Senator John Glenn, 6 flights to the space station, and the final shuttle space mission in 2011. So you can trace a direct line from that final shuttle flight to the first flight of SLS. We've worked with our partners at Aerojet Rocketdyne to upgrade the 16 shuttle main engines, which will power the first 4 Artemis flights. And now we're building 24 new engines using 3D printing and other manufacturing innovations to reduce cost, complexity, and manufacturing time. Of course, all of this work is building towards that Artemis 1 launch from Kennedy Space Center later this year. Here's a closer look at that mission and how it paves the way for future exploration beyond.
3, 2, 1, 0. Mission liftoff.
Artemis 1 will lift off from Launch Pad 39B at NASA's Kennedy Space Center in Florida with 8.8 million pounds of thrust, provided by the most powerful rocket in the world, our Space Launch System rocket, or SLS. The uncrewed flight will be the first integrated test of SLS, our new Orion spacecraft, and exploration ground systems at Kennedy. Artemis 1 will send Orion beyond the moon, 280,000 miles from Earth, farther than any human spacecraft has ever flown.
This is not NASA doing this. This is the United States of America doing this program, the Artemis program, and there are companies all across our country that have a part in it, so there is kind of this wave of excitement being generated just by saying, we're going back to the moon.
After the upper stage of the rocket separates from Orion, the upper stage will deploy small satellites over several days to perform science experiments and technology demonstrations. Orion will make its multi-day outbound trip to the moon, propelled by a service module provided by the European Space Agency. Engineers will test Orion's systems on the way to the moon. Then, Orion will fly about 60 miles above the lunar surface, using the moon's gravity and engines on the service module to enter a lunar orbit. After about a month and a total distance of over 1 million miles, Orion will return home, faster and hotter than any spacecraft has before. A primary goal of Artemis 1, ensure Orion safely returns to Earth before we fly with humans. When we do, we'll build our capability for sustainable lunar exploration, preparing us for missions farther into the solar system.
Initially, what we'd like to do is start establishing a presence on the moon. So we're going to establish going back there on a regular basis, and then we'll end up setting up Gateway, and we would launch to the Gateway, and from Gateway, land on the surface of the moon.
We are there for, weeks, months on end. And there, we're going to be able to test out all the hardware and the habitats and the hatches and the suits and the rovers that'll allow us to prove out those technologies. The moon will lead the way to Mars, and we should be there, within the next couple of decades.
Just amazing. And now we are going to hand things over to Catherine and Bill again in the control center. Catherine?
Thanks, Lee. We are in the secondary test control and outside the control room here listening in so that we can provide you updates. Bill, can you give us an update on how things are progressing?
Yeah, so they're in the process now of going through the final checks. Everything's really nicely going really great today. So everything's right on schedule, nominal. They're trying to do this thing what they call right now is jump the clock, which is trying to work it a little bit ahead. So they're in the process of resetting the clock and making sure that when they get to that 10-minute point that it doesn't continue to count down, because that's where they have to go with that pole well ahead of that. So they're working on setting that stuff up right now.
All right, so we'll continue to stand by and listen and provide updates. And as Lee mentioned earlier, the team previously conducted a hot fire test in January. The engines did shut down earlier than planned during that test, but the January 16th test successfully completed several operations for the first time. They were able to transition to the automated launch sequence operated by the core stage flight computer and the green run test software. They completed the terminal countdown sequence that is like the launch countdown. They also pressurized the tanks and delivered the propellant to the engines and demonstrated the performance of the core stage as main propulsion system, firing the engines at 109% power, and they operated the thrust vector control system that steers the engines. So it's a smooth countdown so far today, and we'll keep standing by. We'll take a pause for a moment, and we'll check back in just a few minutes. The B1, B2 test stand that you're seeing there is a dual position vertical firing facility with the B1 side equipped for single engine tests and the B2 side designed for rocket stages. The stand is anchored to the ground with 144 feet of steel and concrete. We talked a little bit about the history of the RS-25 engines, and the B2 stand, which is where the SLS core stage is secured now, also has quite a bit of history. It was used in the 1960s to test Saturn V rocket stages that carried humans to the moon during the Apollo program, and the Space Shuttle main propulsion test article, consisting of an external tank and 3 main engines linked together with a simulated shuttle orbiter, was also tested on the B2 stand. The B2 stand has been modified to test the SLS core stage for the Artemis program that will return humans to the moon, with a new steel superstructure added for testing the SLS core stage. The stand is now almost 350 feet high, ranking it as one of the tallest structures in the state of Mississippi. For a little bit more about the RS-25 engines, each of the RS-25 engines is about the size of a compact car if the engine were turned on its side. Standing up, they are each 14 feet tall and 8 feet in diameter. They each weigh about 8,000 pounds. The RS-25 is designed to operate in extreme temperatures from negative 423 degrees Fahrenheit to 6,000 degrees Fahrenheit. And as Lee mentioned, today's test will go from extreme cold to extreme hot. When the hot gases exit the RS-25's nozzle, they travel at 13 times the speed of sound, which is fast enough to travel from Los Angeles to New York City in about 15 minutes. The core stage itself stands 212 feet tall and at a diameter of 27.6 feet and weighs about 2.3 million pounds when loaded with propellants. So the next major milestone coming up will be the poll for the terminal count. It's the last 10 minutes of the countdown. Bill, can you tell us a little bit about what we can expect to hear during the terminal count?
Yeah, so just ahead of terminal count, we'll hopefully get that call. They'll do a poll, which is all the members of the team basically getting their go for going into that terminal count sequencer. And then once we actually get into it, there's at least 500 different events that take place in that last 10 minutes. So I'll not go through each one of those with you, but there are some pretty good ones. To terminate the hydrogen replenish. And then we've also got to go into the hydrogen tank pre-press operations, which is where they'll pressurize the hydrogen tank. It'll start doing that on its own as well. Initiate ground helium spin start supply to the CAPUs. So initially when the CAPUs come up, they'll be running off of the helium supply in the stand, and then it'll switch over to the engines when they come up as part of the plus count. Can you tell us a little bit about what the CAPUs are?
Yeah,
so that's the core stage auxiliary power units. They're variants of the ones that were flown on shuttle. The difference is that where those were hydrazine powered, these are basically run off inert gas and then into hydrogen off of the engines when they get into the plus count. So it's basically it's basically a turbine system that spins a pump, and that pump then in turn pressurizes the oil in that system, and through a series of valves and commands, they can then go ahead and actuate the actuators that are mounted to each of the engines in pitch and yaw. After that, we'll get into liquid oxygen terminate, and liquid oxygen replenish will stop that operation. And then we'll go into CAPU starts, and that's where each one of those core stage auxiliary power units would be powered up. And that takes, on the order of about 30 seconds to bring each one of those units up. They're done individually. And then they basically move into transitioning into the LOX tank pressurization operations. They do a TVC gimbal profile on helium, so that's actually something different that you won't see in the plus count. In other words, we do a lot of actuation of the TVC system in that, but we don't move it as far because of the limits we've got in the stand for how far you're moving it relative to having the engines burning at that time. So in the pre-count, we'll basically get the full movement, the full gimbal, full displacement, and then once they get into the plus count, they will not do that, but they'll do some other things. And then after that's complete, they'll basically bring the actuators into their null positions. But basically, they'll go ahead and make sure the engines are ready to go ahead and start. They will then transition the core stage to internal power. They do have, with the redundant inertial navigation unit, they've got the gyro compass alignment that they'll finish up. And that's when we get into the next big sequence, which is the go for the automated launch sequencer, and that'll start roughly at 33 seconds. So that's kind of the big steps that take place up to that point. And what happens once we get into that ALS is that if we have to recycle, then that's a big deal. It's probably not something we can recover from that easily on day of. But ahead of that, we can basically recycle back to the 10-minute mark, and then it would take us probably an hour or two to get back into position where we go through it again. But that's kind of how the day would look.
Thank you. So it sounds like the majority of the calls are actually going to come in the last 5 minutes of the terminal count. And so we're waiting to hear when we are ready for the poll for the go, no go into the terminal count. So we'll stand by for a little bit here, and then we'll come back when we have another update. For the Artemis 1 launch, there will be a built-in hold before the go-no-go pull to go into the terminal count with the last 10 minutes of the countdown. This isn't quite the same, but it is similar. The team takes a look at the data from the vehicle and the facility and ensures that everything looks good before proceeding into the terminal count. So we're just a little more than 10 minutes away from our T0 time now to fire up the engines. And when those engines fire up, the team is looking to get at least 4 minutes of data to support the test objectives needed to confirm that SLS is ready to launch Artemis missions. From there, they will continue to let the engines fire and to burn through all of the fuel in the tanks and possibly pick up additional data for some secondary test objectives. During launch and ascent for Artemis missions, we expect the engines to fire for about 8 minutes to drain the tanks of the propellant before what is called the main engine cutoff, or MECO. So, Bill, tell us a little bit about what we can expect after hot fire starts.
Okay, so the other thing I'd say is I'm also listening in, so if we get to the point where they're going to call for the poll, I'll just tell you to pick it up at that point. But so where our left off was with ALS start, so that's roughly 30 seconds before they actually start. We would then bring on the hydrogen burn-off igniters, which are basically a series of flares that are built into the stand that pick up any residual hydrogen and basically dissipate all that. They'll finish with the renew redundant inertial alignment navigation mode, and then basically they go into, at roughly 6 minutes, they'll do the RS-25 starts, and those they bring up one at a time, and roughly at 5-6 seconds they'll start that. At 1 second they'll be up and running at 100%, and with that, I think we're getting ready to hear them go for the poll. But as they basically get through that part of it, we'll hear the basically the engines will come up to 109% thrust level, and then we'll go into the first poll at the gimbal profile. So I think what we should do at this point is switch over, if we can, to pick that part of it up.
All right, let's listen in to the poll.
That's the correct time pack as the sequencer steps through there. Reminder to everybody, after we get past 557 and after we terminate LH2 system securing, we only have 2 minutes 35 seconds full time before we have to recycle pack. Also, another reminder to everybody, when we do the switch to internal power, we will get the Christmas tree effect on the avionics screen. So that is normal, that is to be expected. So just remind everybody that we will get that Christmas tree effect once we go into internal power. All right, sequencer, on your command, let's go ahead and initiate the terminal count sequencer for substep alpha and record UTC time, please. Copy.
Okay, T-count has resumed.
And give us a UTC real quick, please.
20, 27, 12.
Copy, 077, 20, 27, 12.
You copy?
T-minus 9 minutes.
All right, it sounds like we actually missed the poll, so we are in the terminal count sequence now, and we are standing by and listening as they progress through their steps.
T-minus 8 minutes. T-minus 7 minutes.
LDAS, place your recorders into continuous.
And we're about 6.5 minutes away from hot fire right now.
And T-minus 6 minutes, starting LH2 securing. T-minus 5 minutes, initiating TVC spin start.
Yeah, so at this point, they basically initiated CAPU start, and basically those will be coming up on helium. They'll go into a what we call a wiggle test, which is where they'll gimbal the engines, and then so that's basically coming up here in just a couple of minutes. On the plus side of that, once we get into the engine starts.
T-minus 4 minutes, CAPU start, starting LO2 securing.
Okay, so LO2 is being secured now, so that they're really moving forward in the plus count here. Still roughly at T minus 3 minutes 42 seconds. And so with that, we should be seeing the TVC gimbal profile here in about half a minute or so. Basically, at this point, they've got the water system all turned on. Maybe we'll see that in some of the views. And that'll basically take care of not only the heat coming off of the engines, but also dampen the tremendous amount of noise that'll be coming off. As mentioned earlier, the hydrogen burn-off igniters will come on at about 12 seconds.
T-minus 3 minutes starting PSN 4.
The inertial navigation mode will be complete at about T-minus 10 seconds. And then basically the enable command for ALS at 9.2 seconds. And then we go into engine start roughly at 6 seconds. Those take about 5 seconds to come up to full operating pressures. And basically at that point, the stage controller will be go for launch or go for test in this case at 2 seconds. And basically we go forward into our profile for the day.
All right, we're coming up on 2
There's
minutes.
There's a gimbal test taking place now.
T-minus 2 minutes.
So the call was they just announced at T-minus 2 minutes, which is basically they have finished the gimbal test with the actuators and they're bringing them back into a null position. And then basically at this point they basically are getting ready for powering up the engines. Again, core stage transitions to internal power at roughly 1 minute and 30 seconds out.
T-minus 1/3, switch to internal power.
And then the Reno gyro compass alignment converges at roughly 1 minute. And then we'll have to go for ALS and clear that polar short at T-minus 33 seconds.
T-minus 1 minute following personnel report. Go, no go for ALS, AEA, TEA,
Go.
AGA,
Go.
REA,
Go.
NEA,
Go.
NTC. Vehicle and B2 systems are go for ALS.
And at this point you see basically the water system has come on full bore.
All right, T-minus 30, we're in ALS.
And you just got the official start of ALS. Next up is the hydrogen burn-off igniters come on at 12 seconds before T0.
H-boys on.
Go for engine start.
H-boys are on and engine starts has been okayed.
And all personnel, we've got engine start and we're to the plus count. All personnel, please continue to monitor your systems and grass is in control. We've got a fire. Go ahead and TS. GPS. I copy that. You cancel that. Okay, I did that TBC for launch profile. Remember?
We're just over 5.5 minutes in the plus lap.
About 6 minutes.
We're coming up on 7 minutes of the plus count.
Keep those 7 minutes. Those 7 minutes, 30 seconds, starting TBC profile levels. Those 8 minutes, and then the TBC profile messages.
All right, so we're just over 8 minutes into the plus count.
Personnel are coming up quickly on the last completion here, and we have a cutoff. All right, REA, can you verify REA on channel 16? REA on channel 16, verify. Safe engine shutdown, please.
Safe engine shutdown.
And you're in post shutdown standby, correct? Okay, all personnel, that takes us to page 656. All personnel go to page 656 to start the post-hot fire shutdown securing operations.
All right.
Okay, all personnel on page
Bill, as you said earlier, as we talked about earlier, the team was hoping to get at least 4 minutes of data. And we All right, they are proceeding with their shutdown procedures now. As we said earlier, the team was hoping to get at least 4 minutes of data, and they did get more than 8 minutes, excuse me. So they should have gotten what they need. The team will obviously need to look at that data, but based on what we've seen, Bill, tell us more about what it looked like to you.
Yeah, so they clearly got the full duration that they were after, which is really great news. And I think you heard the applause. They had, the commanded shutdown, which is exactly what they were looking for. They had no TCC violations, test commit criteria violations that would have prompted an early shutdown. So that was really good news. Clearly there's a lot of data that's going to have to be analyzed. The engineers got to see what worked and what didn't, or what needs to be tweaked and what doesn't. But that said, I think the applause says a lot about how the team feels, that they got through the test, and it looks pretty good right now. Yeah, so there was some, observed burning on the aft end. One of the things that Boeing had done after the last test was to apply a lot of extra cork to the aft end, because we didn't, unfortunately, with this test, right, we're not flying through the thin air as we ascend, and so we knew we were going to have more of that, and that was one of the reasons why they added that. They also put a tape covering over the top of that. We knew that, if the tape gets hot enough, that adhesive layer below the tape surface is going to start burning them, so we clearly saw a lot of that, but there was nothing that prompted shutdown early, which was really good news.
Great, thank you, Bill. I think that's all the updates that we'll have for you here as the team proceeds through their shutdown procedures. So we'll turn it back over to Lee.
Thank you, Catherine. Congratulations to the team. So as the engineers gather the data from today, we look ahead to the next steps. This core stage will be refurbished and sent by barge to our Kennedy Space Center in Florida. There, it will be stacked in the iconic vehicle assembly building with other elements of the SLS rocket, including the twin solid rocket boosters, which our teams have already begun stacking on the mobile launcher. The core stage and boosters will then be stacked with the upper stage and the Orion spacecraft. All of this work putting us on track to roll out to Launch Pad 39B for a liftoff later this year on Artemis 1. We've got several other firsts on the horizon. This year, the first of our commercial lunar payload services, or CLPS missions, begin with 2 companies delivering instruments to the lunar surface. The golf cart-sized Viper rover will search for water at the moon's south pole. And a small CubeSat called Capstone will head to the moon, scouting the orbit to be used on later human missions. Meanwhile, the hardware for the next 2 Artemis missions, which will carry astronauts to the moon, is coming together. The Orion spacecraft for Artemis 2 is down at Kennedy undergoing assembly, and the spacecraft for Artemis 3, as well as the rockets for Artemis 2 and 3, are also being manufactured right now at Michoud. So that wraps it up for us here today. After a major milestone on America's return of astronauts to the lunar surface, a successful test of the core stage of the Space Launch System rocket. Up next, we'll be replaying the test, and we will have a post-test briefing in about 2 hours here on NASA television. We invite you to follow all of our progress online at nasa.gov/Artemis program, or join the conversation online with @NASA-Artemis and @NASA_SLS. Thank you for joining us. And
thanks so much for joining me today. Don't forget to subscribe to my channel, and I hope to see you back again real soon. Check out nasa.gov for results of today's test. Thank you, and take